Hello and welcome back to Ganesh Institute. This is a new series on real analysis, and today our topic is Riemann sum. So before getting into it, we should know about some of the terminologies. For instance, what is a norm or mesh? What do you mean by refinement? What is upper or lower R integral? And then we land up into Riemann sum. Okay, so let's get started.
What do we mean by partitions? Let's say you have I, which is a closed interval AB. Now it is, let's say I is closed and bounded interval. As we can see, it is closed. It has these n positions inclusion, closed and bounded interval. Okay. Now, if I want to have partition means dissection or net. If I want to have the dissection, let's say you have a closed interval 1, 2, or let's say 1, 4, and you want to split this into partitions. You may have 1, 2, 3, 4, or you can again split 1 and 2, 2 and 3, 3 and 4 into infinite numbers, right? But here we don't want infinite. When it comes to dissection, net or partition, so the partition is what? It is a dissection or net of finite set of real numbers. Okay, let's say I'm splitting these two into a partition having x0, x1, x2, and because I want to make it finite, so I'm keeping it xn minus 1 and xn. Okay, now here the condition is, the property is, you will be having A and B at edge positions, right? Because this is a closed set, closed interval, and you have these values in between, right, as partitions. So it is self-explanatory that in between these two you will be having all those numbers in which you have broken this down, but the series is like, okay, x0 is always lesser than x1, x1 is lesser than x2, and so on so forth. You will be having so many values here. So P is having the segments of partition. Now if someone asks me what can be the length of this segment, length of P, then I'll say the segment is, for example, if I have xr minus 1 and xr, let's say I have, this is the length, so I'll denote it by the change, final minus initial value of the interval, and r can be anything, 0, 1, 2, 3 and so on. Not 0, because you cannot have 0 and minus 1. It should start from where r can be 1, 2, 3 and so on up till n. Okay, so this is how you calculate the length. Next up, the terminology which we require to solve some of the questions, we have norm or mesh. You know how to find norm? So basically we have partition P. If we find out the norm of this P, or we should say greatest of the lengths greatest of the lengths of P. See, I have x0, x1, x2. For these two, the length will be x1 minus x0, correct? For these two, we'll be having xn minus 1. So whichever is the greatest, that will be the mesh. So I would write it in the form of set. So I have P norm, I would say the maximum value of the length, where this R can range from 1 to n, correct? Sometimes we use it as P and sometimes we write it as mu P. So mu P is also referring to norm and mesh, norm or mesh. Next thing which you should learn about is refinement. What do you mean by refinement? Now let's say I have got another partition P star. I'll say this is the refinement of P when P star is finer than P. So let's say I'm dividing this P. For example, I have divided this 1, 4 into 1, 2, 3, 4. But I can make it more finer. I can have 1, when we find out infinite rational numbers between two numbers, right? What we do? 1 plus 2 by 2. 3 by 2 is in between these two. Similarly, we can find out as many as we want. So if I keep going and get a finer partition, that will be my refinement. So this P star, the condition is this can only be done if this is the condition. Okay? Always when we write it as, let's say, right, we'll be having this sort of condition when you are using every point of P for its construction. Okay, let's say you have P1, P2 as two of the partitions. Then the common refinement between these will be P1 union P2, because of course this is the case. Okay, P star is greater, a bigger set than P. Okay, you will be having more elements in it than P, so it is bigger, right? Though you have made it from P only, but you have refined it and you have got many elements, so P has become the subset of P star, and hence we are getting this refinement. Okay, now let's come to the main topic, which is Riemann sums, and because of these we have read so far whatever we have read. Okay, what do you mean by Riemann sums? Let's say you have a function. Now we are talking about function. This function is again bounded function. If it is bounded, then we must be having closed interval. So let's say this function is bounded function defined on a closed interval a, b, and I have divided this a and b into a partition set x0, x1, x2 and so on. Okay, now I need to find out two things. First, infimum. Second, supremum. How would I do that? do that? See, for infimum, I need to take the value of fx. I can take any of two values. For example, I have x and I have divided x into xr, and lower value is xr minus 1. So which one is infimum? Whichever is infimum out of these, you will select that, and that will become your mr, small mr. And if you want to have supremum, then you will require supremum of fx. Only thing is to define the interval you are taking. So again, this is the lower limit, this is the upper limit. You are dividing this x, where r can be anything from 1 to n. This is 1, okay? Okay, so the bigger value out of these will come and marked as capital MR, and lower value small mr. Now in order to find out Riemann sums, you will consider Riemann sum is divided into two values: lower Riemann sum and upper Riemann sum. Okay, so when we say lower Riemann sum, I'll be having lower of partition of function. It will be having all the values from 1 to n, but because it is lower, I'll take infimum value and I'll multiply it with the length. Okay, the change, final minus initial. Similarly, guess what will be having in upper Riemann? Upper of partition of function, again are ranging from n1 to n. I'll be having supremum value and again the change. So I'll say that this is the lower Riemann sum of f on the interval AB, closed interval AB, with respect to the partition P, and this is the upper Riemann sum. Okay, now one more terminology which you should know, that this lower Riemann sum is also known as lower Darboux sum, and this upper Riemann sum is also called as upper Darboux sum. We will talk about Darboux theorem in a bit. So these are the values of lower and upper Riemann sum. Have you got it? Remember, whenever you have lower and upper sums, upper R sums, R is the short form of Riemann, the condition is always lower one is lesser, has to be lesser or equal to upper one. And if you want to have negative of function, then the upper will become equal with negative sign, and similarly vice versa. If you take negative function with upper, it will be equal to lower of negative lower of partition. Okay, remember that family of all partitions of this interval A and B will be represented as PAB. Okay, now what do we require? So there are a series of theorem in it in order to get into the question, so you should remember that. So first theorem on Riemann sum is, suppose you have f, this is theorem 1. Suppose you have f, a bounded function, and it is defined on a closed interval. Again, this is the common condition AB, and you have already talked about m and m. This is the upper this is supremum value of fx and this is the infimum value of fx. Then the theorem states that for any partition of AB, you will be having infimum of B minus A always lesser than the lower R sum, which is always lesser than, if I apply this one, and this, the biggest value out of these is supremum of the change. So the first theorem states that infimum of the changes in the interval is the lowest value and the supremum is the maximum value, and these two fits in between. Okay, and if I have to fit refinement, then I would say lower is bigger, because refinement is opposite. Lower of P star, that is refinement of P, is greater than P, because of course P star is a bigger set, and if you have to take supremum value, then it becomes vice versa. Okay, this is another theorem. So if I have to apply this in a form of a question, so here it is. Where has it gone? Here. Okay. Read this question. Show that if f is defined on AB. So again, I have understood that function is given which is bounded and closed. Function's value is given, fx is equal to k, and this x belongs to this interval. K is any constant and function belongs to Riemann R values of AB. You need to show that this is the case, Riemann value, and the integral, if I have to find, this is equals to kb minus a. Okay, now because it is talking about integrals, so we need to talk about, so far we have talked about Riemann sums. Now if I explain what do you mean by lower and upper are integrals, Riemann integrals, how do we calculate them? So again you have seen condition, f is a bounded function, it has a closed interval AB, so we have set of LPF. If it is lower R sum, then definitely it is bounded above MB minus A, right? Why? Because this value is greater. We just talked about the series, right? This series. Similarly, so this one is bounded above. So if it is bounded above, it will be having supremum of LPF. Okay, bounded above means supremum, bounded below is infimum. So if you have lower R integral, okay, then or we say lower Riemann integral, if you have to find out, that will be supremum of LPF. Okay, how would you write it? Integration of limit a bar to b fx dx. Okay, it is denoted by this lower R integral. Lower R integral. denoted by this. Lower because we have marked the bar here. Then if you have to find out upper R integral, upper R integral will be having infimum of, because it is bounded below MB minus A. So it will be infimum, but infimum of what? Because it is upper. So infimum of upper value, upper PF. Okay. How do we write it? Here we have limit here. Now we will be having the limit A, B bar, because it is upper integral fx dx. Okay, fx dx. How would we calculate? Simply learn that or remember this supremum and infimum. Sometimes we get confused. Just find this trick out, that for lower, if you have to find out lower R integral, you will use supremum of LPF. If you need to find out upper R integral, you will use infimum. Are we ready for the question? Let's see. So because they are talking about the integral value, so we will see how we can do it. So first of all, we would write the partitions. Let's say I have divided A and B into many partition like x0, x1 and so on up till xn. Okay. So firstly I have got my partition for AB in closed interval. Now I need to find out both of the integral values. I have this AB bar. Tell me whether it is lower or upper R integral. Yes, it is upper. If it is upper R integral, what would we use for integration? That's right, infimum. Infimum of what? Infimum of upper value. Now upper value, how do we write? The function with the change. K delta x1, K delta x2 and so on. K delta xn. So that means infimum, if I take out this K, I'll be having all the lengths with me. Delta xn. Okay. Can I write, because these are the change values. So ultimately everything will get cancelled out and I would get the change only. That is B minus A. So infimum of KB minus A is KB minus A only, because it is constant and we are getting the change here. Correct? There is no value from which I can find out that what is infimum. Now if I have to find out lower R integral, I would write A lower bar of F, and for lower R integral I would use supremum of again K delta x1, K delta x2 and so on up till K delta xn. Again supremum, I would take out K as common, delta x1, and again it is giving me same value, isn't it? So supremum of K, this is the change, and it is of course KB minus A. That means because K belongs to RB minus RAB, this integral, this limit, and both of the values are equal. So simply the integration of the function will be KB minus A. Hence proved. Got it or not? So this is how you can use Riemann sums, partition, norm, and mesh to find out the lower and upper R integrals. This was the basic question. We'll do a level up as soon as we go ahead with other videos. So stay tuned.
If you really like this video, then don't forget to like, share and subscribe our channel. Till my next video, take care of yourself. Bye-bye.